We are excited to present game-changing conceptual solutions for waste recycling and management, along with the most cost-effective methods for producing oxygen and green hydrogen both for space and Earth. Our innovative approach harnesses detonation waves to generate supersonic jets of highly superheated steam without relying on external energy. This breakthrough is made possible through our cutting-edge detonation superheater, redefining efficiency and sustainability in the industry. Following this innovation, we introduced the Advanced Waste Recycling and Management System, an advanced solution for deep thermal recycling, transforming waste into synthesis gas and green hydrogen for both space missions and Earth-based applications. To obtain a continuous supersonic highly superheated steam jet, a stoichiometric binary mixture of oxygen and hydrogen, blue arrows, is fed into the annular detonation chamber through injectors, where it is diluted with primary low-parameter steam with a temperature of 100 to 150 degrees Celsius. At the same time, heated feedwater, red arrows, is injected from the internal volume of the cooling container through Hulse turbulators into the annular detonation chamber, where it is converted into primary steam to form a stoichiometric triple mixture of oxygen, hydrogen, and steam, which is ignited by the ignition system using spark plugs. In the annular detonation chamber, continuous detonation combustion of a triple stoichiometric mixture occurs with the formation of a high-frequency continuously rotating detonation waves, that leads to detonation compression and superheating of steam to temperatures of about 2000 degrees Celsius with the formation of a supersonic superheated steam jet. At the same time, longitudinally pulsating detonation waves are generated, which propagate along the detonation channel and enter the outer annular conical cavity of the cooled gas dynamic resonator, made in the form of a Laval nozzle, from which they are repeatedly reflected. The multiple reflected detonation waves interact with the leading longitudinally pulsating detonation waves, implementing the process of multiple shock resonant compression of steam. This results in extremely strong superheating of the steam to a temperature of 3500 degrees Celsius and higher without the use of external energy, in accordance with the Hartmann effect, and the emergence of a continuously supersonic highly overheated jet consisting the mixture of oxygen, hydrogen, and steam, accompanied by shock detonation waves. AWRMS is an advanced waste recycling and management system for deep thermal recycling and converting of waste into synthesis gas and green hydrogen, designated as well for space missions as terrestrial applications. In two detonation superheaters, tangentially and counter-connected to the vortex reactor, supersonic highly overheated steam jets with a temperature of about 3000 degrees Celsius are generated, which are accompanied by shock detonation waves. From the waste preparation system, through the waste supply system, the waste in the form of a suspension is fed to the detonation superheaters. Supersonic highly superheated steam jets pick up waste and feed it tangentially and counter-currently into a vortex reactor, where stable stationary vortex structures are formed, in which aerodynamic fragmentation of waste occurs using shock detonation waves, and under the influence of superheated steam, complete thermal decomposition of waste occurs, forming a synthesis gas flow, which is tangentially fed into a centrifugal vortex cooler separator, where it expands, cools, and undergoes radial stratification in a centrifugal forces field, dividing into two flows. Lighter hydrogen molecules are collected in the central part of the centrifugal vortex cooler separator and cooled. The cooled hydrogen stream is fed to the Sabatier system or another consumer. Heavier carbon monoxide molecules are collected in the peripheral part of the centrifugal vortex cooler separator and cooled. The cooled carbon monoxide stream is fed to the Sabatier system or another consumer. The resulting condensate of aqueous solutions of simple acids and solid non-toxic slag, through the slack and condensate outlet system, are removed from the vortex reactor into a vessel for receiving and storing slag and condensate. Next, the supply of starter gas is stopped, and part of the generated synthesis gas is supplied for its own needs. AWRMS switches to the self-sufficiency operating mode, consuming only oxygen and water from external sources. Electricity consumption from external sources is minimal. External electricity is only needed to ensure the operation of the AWRMS control system, including the high-voltage unit to ensure the operation of the spark plugs in the ignition system, to operate the pumps to ensure the circulation of feedwater in the cooling container,